So the last talk of this session is on fast correlation attacks on grain-like small-stage ciphers, and Willy Meyer is giving the talk.
So I give a brief outline. First, background and motivation. I think I can skip this part because this is already contained in the previous talk. Then I give a brief description of fruit and a more general model, and then I come to a general description of the attack. And then one step, crucial step, is how to prepare parity checks in a fast correlation attack. And then I come to conclusions. So I'm sorry to skip quite some part, because I don't want to repeat. So I come to outlining our contributions. So the study of the security of grain-like small-stage string ciphers by fast correlation attacks. That's the main topic here. And for this we define a generalized model which adopts cascaded structures of NFSRs and essentially two feedback shift registers are involved here. Then we show that if the nonlinear combining function used to generate the final keystream has some pseudo-linear properties, we could restore the full internal state of the model in a divide and conquer manner. Especially for the fruit string cipher, it requires 2 to the 63 fruit encryptions and 2 to the 22 keystream bits for all the 80-bit secret keys. And this has been verified by experiments on a downsized version. So fruit is a grain-like string cipher. It's bit-oriented, and it has an 80-bit secret key and a 70-bit public initial value IV. So as we see, it has a non-linear and a linear register, and it has an output function H, and the feedback function F is linear, the feedback function G is non-linear, and in each update step there is XOR a round key bit. So the 43-bit LFSR is updated independently. That's an important point here, that it's autonomous. It's updated by a linear function f, which is written here, but it's not important how the details work in that case. The NFSR is updated recursively by a nonlinear feedback function g, which is defined by a nonlinear part, which we term g. And so one essential point is here that besides the function g, there is XOR this round key bit kt prime plus a counter bit in at least in some versions of fruit string cipher. The counter bit is known at each position. So there are two counter registers. Actually, the details don't matter that much at this time, but just one essential part here is that the round key bit does look rather intricate here. Actually, they have built in this with the hope that this would prevent key recovery. But we can show that even with this quite complicated round key bit, we can break this cipher, which was a bit maybe unexpected. So if the internal state ST/NT is given at some time, the filter function H is given by HD, which is a rather simple function here. And the keystream bit is generated as CT, which is also which is the sum of this 5 filter function H and some other remaining part. The details of the initialization are not important at this step here. It doesn't move anymore. So what does that mean? Oh yes. A bit delayed. So I come to the generalized model. It looks like virtually every grain-like stream cipher, but again we have some round key bits added here, and the model is really a bit more general, because in grain-like ciphers usually one register is linear, but our attack works even if both registers are non-linear. So again, we have a non-linear part and another part which may be linear or non-linear, and we have some secret key and some round key function and some counter. And some counter bit which is used in the update function. So we have 5 Boolean functions involved in the model: the linear or non-linear Boolean function f, the non-linear function g, and another linear function that maps from one register to the other, and a linear Boolean part and a non-linear Boolean part. The non-linear part is h, the function h. And at each step, the FSR is updated independently by F, but the NFSR is updated by G with a round key bit K prime and a counter bit and some bits of the FSR part. So the round key bits K prime and time T are generated by the round key function RKF, which takes the secret key K as part of its input. So actually there is some technicality here, but I think we can make it easy. We have 2 registers, and we have linear and non-linear parts in the functions involved. So this gives just 4 cases. We needn't deal with all these indices here, but if we write down, we have to be a bit technical, but we can omit it here. So we assume that the round key function is periodic, which is essential. So this means that the round key bits repeat after some period t. So we could even cover the case where the counter bits are completely unknown, but we need also to know the period of this counter bit. Now, a very essential part of our assumption is that the pseudo-linearity. This means essentially, if we fix the state of the autonomous feedback shift register, the output function of the cipher becomes linear in the inputs of the nonlinear part. So this is the case, for example, in grain. So the FSR updates independently, but so for any possible value of the FSR, we get a linearly filtered NFSR, which is a rather particular situation. So grain version 1 fits exactly in this model with the parameters m equals 80 and n prime equals 80, where m and n prime are the lengths of the involved registers. The key size is 80. The cipher root also fits into the model, but with much smaller parameters, namely m the nonlinear register is 37, and the linear one 43, and the key size is 80. It's an interesting point here that Plantlet and Lizard, two other ciphers, we have just heard about Lizard, do not fit into this model thus far, because if we fix the linear, the part of the autonomous register, the output function does not become linear. So I come to some basic observations and ideas. So the FSR, as we see, is updated independently without influence by other part. And this means that for a small stream size, the internal size of the FSR is not too large. So it's conceivable that we can make an exhaustive search on the autonomous register. And combined with the pseudo-linearity of the function h, we could derive some random probabilistic linear system on the initial NFSR variables with quite some high and constant bias. Actually, it's a bit counterintuitive. One would think if you iterate on and on, I think the bias would kind of decrease, but we could find out a method so that the bias remains constant. So in another step, we construct some low-weight parity checks to reduce the dimension of the initial NFSR variables. Actually, we could reduce the number of NFSR variables involved for the search. So we don't solve the parity checks directly, but we construct a distinguisher using the fast Walsh transform, and then the FSR is restored independently of the NFSR. So we can make kind of divide and conquer recovery of the whole internal state. And the internal state of the NFSR can be retrieved in a multipass manner with a complexity much lower than that of recovering the FSR. For the specific ciphers, one period of the round key bits and the original secret key could be derived with a much smaller complexity, using the mechanism of the primitive and the definition of the round key function. Although we have seen it's quite complicated, we managed to recover the secret key. So the outline of our attack can be summarized by this kind of algorithm. So the input are the length of both registers, and D is the data complexity. And input also, of course, we need some segment of known key stream. And in the first phase, we prepare the parity checks, and for each possible value of the LFSR state as 0, we use a method to derive the probabilistic system. Out of this, we construct the parity checks, and in a second phase, we recover the full internal state that matches with a given key stream sequence. Then for each possible value of the FSR, we use a distinguisher to check our choice, and for each pass candidate, we recover the NFSR state part, and we recover also the secret key. So these are the steps of the attack. In a later step, this looks a bit technical, but instead of caring with all these indices, we just do what we have stated in general. We fix some state, and then we get this linearly filtered NFSR. So for fruit, this looks like this here. So we have the output here, and here we can see if we fix the FSR part, it means all these symbols, ST and so on, we see we get a linear function. And an interesting point is here, which is surprising. First is that the secret round key bit has vanished in this procedure. You would think that when you iterate here, that you have always to cope with new round key bits coming in, but it's not the case here, in the way how we do it. we can circumvent the round key bits. So if we do this for fruit, we start with N37, then we use, actually the trick is to use the keystring bit here to get a relation here where the round key bit does not occur. If we iterate this, then we have another such expression where now two keystring bits are involved. So this effect of the round key bits have been masked. And then we can carry this procedure on and on. And another point is now that we have to use linear approximations of the feedback function. Actually, this looks a bit technical, but we can just say we have here this G, this feedback function here, and we replace it by a linear function with some bias. Actually, in proof, we obtained 7 independent linear approximation of quite some bias. So here I think we can ignore mostly these technicalities. The point is here just that we write down these equations in kind of error correcting code manner. But otherwise I think we needn't get all these details. Even here, actually the main point is just the shape of the equations we get here. So it means we have still not, in this kind of approximation, actually the round key bits show up, and we have to get rid of these round key bits. And the funny thing is that we can do this when we do an ordinary, it looks very highly technical, but the idea is just we have this generator matrix and we would like to eliminate part of the entries by adding say 2 columns, maybe by birthday argument or something different, so that these columns part of these columns vanish. So in the search, we needn't search over the full NFSR state, but only over part of it. But the funny thing is that if we XOR two columns, then the secret key bit will vanish. So the attack profile is now quite short here. Make an independent guess, recovery of the FSR state, restore the NFSR state, and recover the secret information within one cycle. Actually, I can skip most of these parts. Actually, it's just a little bit describe what we are doing. These are pictures of the low spectrum, which I have mentioned, and actually we get a very clear peak in the case of the correct choice of the FSR, which we found in experiments of downsized versions. So we can also skip this algorithm 2, which describes how to find the secret information, meaning the user key here. And in this case, we can just enter the parameters of fruit and get in an easy way the secret information. So we could do some complexity analysis. The important point is here that the complexity is definitely lower than 2 to the 80 here. Actually, an interesting thing is that we get 2 new design criteria, namely the pseudolinearity of the output function should be avoided, and there shouldn't be large enough linear approximations of the feedback function of the NFSR. So actually, this is just an example of a downsized version of the experiment, but we needn't go into detail here, so we come to conclusions. So we have studied the security of grain-like small-state string ciphers by fast correlation attacks, and the interesting thing is that the relatively traditional method still works, and we have worked out a more formal framework for fast correlation attacks that uses the divide and conquer strategy on the general model. And we have seen if the nonlinear combining function has some pseudo-linear property, then we can really build this attack, especially if the correlations of the peak function are large enough. And we have broken fruit, a tweaked version of Sprout, means 2 to the 33 fruit encryptions, given 2 to the 22 keystring bits for all the keys, which clearly violates the security claim. So our results have been verified by experiments in the downsized version. Thank you for your attention.
Thanks. Are there any questions? I have one, Willie. So how with certain key size, how big have the states got to be in order to resist the attacks? Which ratio would you propose?
Well, the key size of which cipher then?
So for a key K, how do you have a ratio of the states in order to resist, or?
Actually, it worked for all keys.
Mm-hmm.
So that's one point. Actually, we had another attack that exploits the special structure of this round key function, but I think it would work for totally different round key functions.
So can you say a small state? When does the state stop being small?
Yes, actually that's a good point. For example, Cloudland, for example, has already a size of 61 or 60, the sharp part, then it won't work anymore. But 43 is just on the verge, so that it can work. So the size of the register. So if you decrease the state size a bit, then you could also avoid this kind of attack.
Thank you. Any more questions? Okay, so then let's thank Willie again and all the speakers of this session. There's a coffee break after.